So imagine a U.S. Air Force C-17 cargo plane, right? Just dropping a massive 100-megawatt battery onto this completely remote Pacific island.
Which, I mean, sounds completely like sci-fi.
It really does. But now imagine that exact same deployable battery tech is what's going to be charging your neighborhood delivery vans next year.
Yeah, that's the reality of where we're at.
Right. Because the public narrative right now insists that the electric vehicle revolution is, stalling out. But the physical reality on the ground is looking a lot more like a high-tech arms race. So welcome to the deep dive. Today, we are completely stepping away from the narrative whiplash.
Definitely.
We're looking strictly at the hidden physical backbone of it all, which is the charging infrastructure.
And we have an incredibly diverse stack of sources for you today to build this picture.
Oh, yeah, tell them what we've got.
So we're pulling from fresh 2025 and 2026 industry data from the EV analytics firm Perrin.
Right.
We also have these really deep dive academic reliability studies from OSTI, which is the government's Office of Scientific and Technical Information.
And we pair that with a federal watchdog report from the GAO, right?
Exactly. Plus, those genuinely surprising military press releases you mentioned from the U.S. Air Force.
Yeah. The military stuff is wild.
Yeah.
But our mission for you today is basically to provide a massive reality check.
A physical reality check, yeah.
Right. We're going to explore the mechanics behind the scale of new commercial deployments, the frustrating engineering reality of why your local plug might be broken.
Even when the app says it works perfectly.
Yes, exactly. All the way out to those off-grid mobile power solutions that are blurring the line between civilian logistics and national defense.
Because it's a sector that sits, like, squarely at the intersection of heavy physical infrastructure and high-speed software. And the friction between those two worlds is where the real story is actually happening.
Right. And to see that story, you really have to look past the headlines about adoption slowdowns. Because, if you think about the charging industry, like a railroad company laying down train tracks, right?
Yeah, good analogy.
You would expect them to dramatically slow down construction if they thought fewer trains were coming down the line.
You'd think so, yeah.
But the analytics from Perrin show they are laying track faster than ever.
The deployment pace is actually staggering when you look at the raw numbers. For the full year of 2025, U.S. networks added over 18,000 new DC fast charging ports.
Oh, wow. 18,000.
Yeah. That represents a 30% year-over-year increase in infrastructure deployment.
30%.
And crucially, it wasn't just like speculative building. The consumer demand matched it almost perfectly.
Right. Really?
Oh, yeah. In 2025, the U.S. fast charging networks saw a record 141 million charging sessions.
Jeez.
Which, yeah, is also up roughly 30% year over year.
So a 30% jump in heavy, capital-intensive infrastructure, perfectly matched by a 30% jump in actual usage. That fundamentally contradicts the idea that the industry is pausing to wait and see what consumers do. But if we pull back from the U.S. for a second, you can clearly see how international regulatory mechanics are essentially forcing this momentum globally.
Yeah, that global context is essential. Like if you look at the UK market using the Fleet 200 data, you see a total transformation in corporate behavior.
Right.
In 2021, large UK commercial fleets were running about 68.3% diesel vehicles and only 8.8% EV.
Okay.
But you fast forward just 4 years to 2025, and that completely inverted.
That's crazy.
Yeah, those fleets are now 15.7% diesel and 65.1% EV.
Well, and that level of capital turnover in massive corporate fleets, that doesn't happen just because of good PR.
Oh, no, not at all.
It happens because of raw financial mechanics, because the UK implemented the Zero Emission Vehicle, or ZEV, mandate.
Is the EV mandate.
Which requires 33% of new cars to be zero emission by 2026. But it's the enforcement mechanism that is actually driving this.
The fine.
Yes, the fines. It's a £15,000 fine per non-compliant car.
It's massive.
Right. Like, if a logistics company is buying a fleet of 100 vans, a £1.5 million penalty completely obliterates the lifetime ROI of running diesel.
Absolutely obliterates.
It makes building out the charging backbone a matter of pure financial survival.
Precisely. Because when global markets institute penalties that severe, the corporate transition becomes completely locked in.
Right.
And that capital expenditure spills over into global infrastructure momentum. The supply chains for the chargers, the software platforms managing them, they all have to scale up to survive.
But looking back at the U.S. market, with 18,000 new ports built in a single year, the obvious concern I have is efficiency.
Sure.
Because, I mean, we've all driven past charging stations and random parking lots that look entirely abandoned.
Oh, yeah, the empty chargers.
Right. So it begs the question, are these operators just blanketing the map with hardware to hit quotas, regardless of actual local demand?
Well, the utilization data paints a much more calculated picture than you'd think. Nationally, utilization, which is the percentage of time a charger is actively dispensing power, is hovering right around 16.4%.
Okay, but 16.4%.
Yeah.
On paper, that seems like a massive underutilization of incredibly expensive hardware.
It sounds low, I know. But until you understand the physical and financial limits of the hardware, it's misleading.
How so?
Well, you actually do not want a station running at 50% or 80% utilization.
Really?
Yeah, because the financial sweet spot for an operator to turn a profit without causing severe wear and tear on the grid components is way lower.
Oh, interesting.
And more importantly, it's about avoiding absolute gridlock and massive wait lines for drivers. So the sweet spot is actually about 200 to 220 sessions per port per month.
Okay.
It's a highly delicate queuing theory problem.
So it's essentially the same logic as a supermarket checkout lane. Like, if the lanes are at 100% utilization, it means the line of angry customers stretches all the way back into the dairy aisle.
That is a perfect way to look at it. And the utilization is intensely regional, too.
Right.
In highly dense urban environments, like Washington, D.C., chargers are processing 12.3 sessions per port every single day.
Wow, every day.
Every day. They're operating at the absolute limit of that sweet spot.
Jeez.
Conversely, in a sprawling area like Alaska, a port might only see 1.1 sessions per day. So the national average of 16.4% masks the reality that operators are surgically placing these high-capacity stations exactly where the localized grid demand is peaking.
Right. But if utilization is peaking in those dense areas, the immediate problem becomes one of scale. Because the National Renewable Energy Lab states we need 1.2 million ports by 2030 to support the broader transition.
Yeah, that's a huge target.
And as of May 2025, we only have about 219,000.
Not even close.
No. So bridging that gap requires an astronomical amount of capital, which forces us to look at where the funding is actually coming from right now. Is the government paying for all this?
So this is where the July 2025 Government Accountability Office, or GAO, report becomes really critical.
Okay.
They scrutinized the $7.5 billion from the Infrastructure Investment and Jobs Act, the IIJA.
Right, I remember that.
Yeah, it was a massive pool of federal money specifically allocated for the NEVI, that's the National Electric Vehicle Infrastructure and CFI charging programs.
Because it was positioned as the government providing the ultimate financial catalyst to build out this network, right?
Right. The intention was definitely there. But the operational reality was a severe bottleneck.
What happened?
By April 2025, out of that whole $7.5 billion initiative, only 384 NEVI and CFI-funded chargers were actually open to the public.
Right. 384 chargers.
Yep, just 304.
That is a stunning ratio of red tape to actual concrete poured.
It really is.
Yeah.
To put that in perspective, Perrin's data shows that now EVI funds were responsible for only about 3% of all new ports built in the entirety of 2025.
3%. Wow. And looking at the timeline in the GAO report, we hit a massive political shift in how those funds were handled.
We did.
And just to be explicitly clear for you listening, we are strictly looking at the timeline of documented events here. We are absolutely not taking any political sides or endorsing any viewpoints.
Right, exactly.
We're just reporting the facts from the sources. And the facts show that the federal pipeline essentially halted.
Yes, sticking strictly to the documented administrative timeline here, on January 20, 2025, the new administration issued an executive order pausing the disbursement of all remaining IIJA funds.
Okay.
They wanted to review them for alignment with their specific policy goals.
Sure.
But as a direct consequence of that pause, the Federal Highway Administration rescinded its guidance for the NEVI program. Then, the Joint Office of Energy and Transportation, which was serving as the central nervous system for technical assistance to the states, they underwent massive staff reductions.
Wow.
And finally, the president's FY 2026 budget proposed canceling $6 billion in those IIJA funds entirely.
So while the federal funding apparatus was effectively frozen in review and structural changes, the private sector was already sprinting ahead.
Oh, they were flying.
It's deeply ironic, right? The biggest physical boom in charging infrastructure we have ever seen happened precisely when the highly publicized federal funding was paused.
It is ironic, but the private market recognized the demand metrics we discussed earlier. They simply couldn't afford to wait for federal grant pipelines to unclog. They just took the wheel.
And, I mean, you can't discuss the private sector without analyzing the undisputed center of gravity here, which is Tesla.
Obviously, Tesla remains the heavyweight champion of deployment.
Yeah.
As of early 2026, they operate 36,877 supercharger stalls.
That's insane.
It is. That represents 51.6% of the entire U.S. market.
More than half.
Yeah. They have the advantage of total vertical integration. I mean, they build the cars, the chargers, and the software that links them all together.
Right. And the physical footprint they're establishing is just massive. Like, looking at the source data, Tesla's largest single site is in Lost Hills, California, and it has a staggering 164 fast-charging ports.
Yeah, a single site.
164. The sheer electrical engineering required to manage the grid connection for 164 high-speed ports simultaneously, that is a marvel on its own.
It's essentially a mega station.
Yeah.
But, the broader industry trend is actually shifting. Yeah. Despite building 164 port stations, Tesla's market share of new deployments in 2025 actually shrank to 37.6%.
Oh, wow. So the rest of the industry is pouring capital in to catch up.
Exactly. Non-Tesla networks like Electrify America, EVgo, and ChargePoint are scaling at unprecedented rates.
Well, and it's not just about putting more plugs in the ground, right? The architecture of the stations themselves is evolving.
Very much so. We're seeing a big shift from those old utility-style installations.
Right, like the lone plug in the dark corner of a big box store parking lot.
Yes, exactly. We're moving away from that and toward destination architecture.
Okay, what's an example of that?
Take Iona, for example. They're a joint venture backed by several major global automakers.
Mm-hmm.
They just celebrated their second anniversary by passing the 1,000 port milestone.
Nice.
But more tellingly, they are opening an automated Amazon Just Walk Out convenience store deeply integrated into a new charging plaza in Dallas.
Oh, that's smart. They are monetizing the 20 minutes you spend waiting.
Exactly.
Because if the car is charging, the driver is a captive audience.
Yep.
But the actual charging speeds are drastically increasing too, which reduces that wait time.
Yeah, the technology is rapidly maturing. 51% of all new ports deployed in late 2025 are pushing 250 kilowatts of power or more.
Oh, wow. So they're fast.
Super fast. We are effectively phasing out the early generation of 50 kilowatt fast chargers in favor of ultra-fast architecture.
Thank goodness.
Right. And additionally, those NECS plugs, the standardized Tesla-style connectors, they now account for 18% of new deployments at non-Tesla stations.
So the fragmented hardware landscape is finally consolidating around a single superior connector.
Finally, yes.
Okay, so the hardware is getting heavier, the speeds are getting faster, and the amenities are richer. The immediate question for the driver is how that massive capital investment impacts the price at the plug.
Well, the pricing data offers a surprising level of stability, actually.
Really?
Yeah, the national average has settled between 45 cents and 53 cents per kilowatt hour.
Okay.
Furthermore, 80% of networks are sticking to fixed pricing models. They're choosing to absorb wholesale energy fluctuations rather than frustrating consumers with complex variable surge pricing.
That's a relief. But the grid is not a uniform monolith, right? The price of moving electricity is bound by the constraints of local infrastructure.
Exactly. If you live in a supply-constrained geographical area, the premium is steep.
Like where?
Well, Hawaii, due to its isolated island grid, averages 86 cents per kilowatt hour.
Yikes.
Yeah, but New Jersey is perhaps the most fascinating case study, sitting at 63 cents per kilowatt hour.
Wait, New Jersey has a robust, highly connected regional grid. Why are they paying island prices?
It comes down to competing industrial demand.
Okay.
New Jersey is currently experiencing massive grid strain due to a rapid influx of new AI data centers.
Oh, of course, AI.
Yep. These data centers require staggering amounts of continuous baseload power. And EV fast chargers, which require sudden, massive spikes of power when a vehicle plugs in, they are now forced to compete for the same highly limited local substation capacity.
That is a wild intersection of technologies.
It really is.
The cost to charge your vehicle in New Jersey is spiking because a server farm down the road is generating language models and images.
Pretty much.
It really highlights how fragile the local grid capacity truly is. Which brings us to arguably the most frustrating reality for the consumer.
Oh, yeah.
Because private capital is building these incredible high-speed plazas, but what happens when you pull up to one and the physical infrastructure simply fails to deliver?
Right, the broken plug epidemic. This systemic failure rate is comprehensively documented in a 2023 study by researchers at UC Berkeley and the SLAC National Accelerator Laboratory.
This was the one published through OSTI, right?
Yes, they conducted an extensive field evaluation of 655 open public DC fast chargers across the 9 counties of the San Francisco Bay Area.
And San Francisco is essentially the proving ground for EV adoption, so if the infrastructure cannot be maintained there, it signals a massive operational flaw globally.
Exactly. And the core issue they found is a massive discrepancy in reporting.
What do you mean?
Well, the charging networks routinely report an uptime of 95 to 98% to regulators and on their public apps.
Sure, you see that everywhere.
But the researchers didn't rely on the app data. They took cars like the Chevy Bolt, Kia Niro, and Porsche Taycan, and they physically drove to these stations.
Boots on the ground.
Exactly. Attempting to initiate just a 2-minute charge to verify functionality.
And the physical reality completely shattered the software metrics, didn't it?
It really did. They found that only 73.3% of the chargers were actually functional.
73.3%. That means over a quarter of the infrastructure was dead on arrival.
Yeah, and the breakdown by network is even more severe. It varied wildly by operator.
Give me the numbers.
So, ChargePoint exhibited a 36.4% failure rate in this field test.
Wow, over a third.
Yeah. EVgo showed a 25.1% failure rate, and Electrify America sat at 20.6%.
So how does a network legally and publicly claim 98% uptime when the physical hardware is failing nearly 30% of the time?
Right. Well, it exposes a fundamental flaw in the engineering protocols of how uptime is defined.
Okay, explain that.
The networks largely rely on automated software pings using the Open ChargePoint protocol. So the internal computer inside the charger sends a continuous handshake to the central server saying, I am receiving power from the local grid, and my internal logic board is functioning.
Right.
To the central software system, that charger is 100% operational.
Got it. So it's essentially like a restaurant claiming they are fully open because the neon sign in the window is illuminated, completely blind to the fact that the registers are frozen and the front door is padlocked.
That's exactly it. The software protocol cannot perceive physical degradation.
Right.
When the researchers stood in front of the machines, they found that 23.5% of the total failures were due to localized physical issues that the software simply couldn't detect.
Like what kind of issues?
We're talking about completely blank or unresponsive LCD screens, internal payment system crashes that wouldn't read credit cards, or physical connectors that had been dropped and structurally shattered.
Oh man, yeah. Anyone who has driven a non-Tesla vehicle knows the physical geometry of these stations can be an absolute nightmare too. And the study actually quantified that specific frustration, right?
They did. In 3.2% of the attempted charges, the physical cable was simply too short to reach the charge port on the specific geometry of the Chevy Bolt.
Oh my God.
So the software says the charger is perfect, the screen works, the payment processes, but the physical cord literally cannot span the distance to the car.
That is so frustrating. The software physically cannot measure real-world hardware incompatibility.
Nope.
It highlights the desperate need for verifiable, standardized metrics that actually reflect the human experience of attempting to transfer power rather than just a server handshake.
Absolutely.
But, you know, if we synthesize all of these friction points, the massive capital requirements, the multi-year delays in local permitting and trenching, the grid constraints causing price spikes in places like New Jersey, the ultimate bottleneck is almost always the physical electrical grid itself.
Yeah, it always comes back to the grid.
Right, because upgrading a commercial bus depot to handle a 2-megawatt draw can take years of utility negotiations and heavy construction.
Yeah, that structural delay is exactly why the bleeding edge of the industry is looking at ways to decouple from the permanent grid entirely.
Okay, this is the part I find fascinating.
Yeah, we're seeing a massive push into off-grid mobile power architectures. A prime commercial example is a company called Exos.
XOS, right?
Right. They recently secured a $3 million contract from an autonomous fleet operator to deploy 12 of what they term charger hubs.
Yeah, I was looking into the mechanics of these charger hubs, and my immediate thought was, why tow a battery instead of just plugging into the local power lines?
Sure, it seems counterintuitive at first.
But then when you consider those multi-year trenching delays you mentioned, it makes total sense.
It is a brilliant bypass of the utility bottleneck. These charger hubs are essentially massive battery packs storing up to 630 kilowatt hours of energy.
Wow.
And they're built directly onto heavy-duty trailers. They can be towed by a standard commercial pickup truck.
So no construction.
None. There was no trenching through concrete, no waiting for local municipal permits, and no negotiating for a substation upgrade.
That's wild.
The fleet operator simply tows these massive energy reserves to the exact lot where the autonomous vehicles are staging, drops them off, and initiates high-speed charging immediately.
It solves the logistics problem for civilian delivery fleets perfectly. But the most revealing source in our stack isn't focused on delivery vans.
Well, the military angle.
Yes, it's a dispatch from the U.S. Air Force Global Strike Command. They hosted a commercial capabilities showcase down in Bossier City, Louisiana, and they specifically brought in companies like Exos to demonstrate these exact same towable mobile chargers. Now, why on earth is the Air Force looking at civilian delivery tech?
Well, because the core engineering problem of fleet logistics translates perfectly to national defense strategy.
Really?
Yeah, the military is heavily focused on operational resilience in austere, highly contested environments.
So we are talking about projecting power into places like remote islands in the Indo-Pacific where there is no existing electrical grid to plug into.
Right, or where the existing grid is a prime target for enemies.
It's
Another company presenting at that showcase, Critical Loop, is engineering mobile microgrids capable of scaling up to an astonishing 100 megawatts of power.
100 megawatts. That is not charging a fleet of vehicles. That is enough localized power to run a small city.
Yep. And the strategic pitch is that these 100-megawatt modular microgrids can be loaded directly onto a C-17 cargo plane.
Unbelievable.
They can be flown into a remote theater, dropped onto an island, and be entirely self-sufficient.
Wow.
They're powering up advanced radar systems, drone fleets, and an entire military installation within a matter of hours.
And it creates a completely closed-loop system.
That is the crucial defense application. By operating an independent mobile microgrid, it provides instantaneous power regulation. But more importantly, it completely insulates the installation against state-sponsored cyber attacks that target vulnerable, fixed local grids.
So the engineering line between managing a civilian autonomous delivery fleet and executing a global defense strategy has completely dissolved.
Totally dissolved. They both require massive, rapid, reliable power that is entirely independent of fragile, permanent infrastructure.
Man, okay, let's pull all of this together for everyone listening.
Good idea.
We started by examining the sheer velocity of the private market, laying down thousands of ultra-fast chargers and constructing 164 port megastations.
All, even as billions in federal funding remain tangled in administrative pauses.
Exactly. Then we explored the engineering disconnect between a network claiming 98% uptime while a driver stands in a parking lot holding a shattered plug.
Or a cable that is 2 feet too short.
Right. And finally, we tracked how the multi-year delays in local grid upgrades are forcing both commercial fleets and the U.S. Air Force to embrace massive deployable battery hubs.
It is a profound structural shift in how we think about energy distribution.
It really is.
And it leaves us with an incredibly provocative concept to mull over. Right now, our entire mental model of EV infrastructure, and really infrastructure in general, is based on static destinations.
Right, the charger is a fixed point on a map. You have to drive your vehicle to the energy.
Exactly. But when you look at the trajectory of Exa's towable hubs and Critical Loop's deployable 100-megawatt microgrids, it forces you to ask a bigger question.
Which is?
What if the future of the power grid isn't a fixed concrete web of wires at all?
Whoa, you were talking about untethering the grid from the ground.
Yeah. Imagine a world where the power grid is completely nomadic.
Okay, paint that picture for me.
So instead of waiting a decade to build high-voltage transmission lines to a new factory or a growing city, we rely on a fluid living fleet of massive autonomous batteries.
Like roaming energy herds?
Yes. This fleet constantly migrates across the highway system, moving dynamically to wherever human demand spikes.
Oh, I see. Whether that is a massive music festival in the desert, a seasonal agricultural harvest, or a coastal city where a natural disaster has just severed the local power lines.
Exactly. The energy infrastructure becomes something that physically migrates to you, precisely when and where you need it most.
A living, breathing, migrating power grid. It is as if the train tracks we discussed at the very beginning aren't just carrying the fuel. The tracks themselves can pack up and drive to wherever the train happens to be.
It completely rewrites the logistics of human energy.
That is a brilliant and staggering thought to leave on. Thank you so much for joining us on this deep dive. Keep questioning the physical systems built around you, look closely at how the world actually works beneath the headlines, and we will catch you on the next one.